Welcome to the deep dive. Today, we're plunging into something you probably think is, well, completely understood. Water.
H2O, right. Simple stuff.
Exactly. We see it everywhere: rain, drinks, ice. But it turns out water almost never behaves quite like you'd expect.
That's true, like how a pond freezes from the top down.
hmm
Seems obvious, but
But zoom in, way down to the molecules, and the story gets really complex, full of these hidden twists. It really shows how even everyday things hold these amazing secrets. And today, that's our mission, to explore one of those secrets. A brand new, really unusual form of ice scientists just found. They're calling it Ice Zero.
Ice Zero. Intriguing name.
Isn't it? So we're going to unpack what makes it special, why it stayed hidden for so long even though it's everywhere, and why it's like super short life matters for everything from clouds to your freezer. This is the deep dive into the research you've shared with us. We're really glad you're joining us. And hey, if you enjoy getting to the bottom of stuff like this, do us a favor. Hit that like button, subscribe so you catch our future dives, and maybe drop a comment. Let us know what other fascinating topics you think we should tackle.
Definitely. And, to add to the mystery, that ice that we all know, the hexagonal kind in snowflakes or ice cubes,
Yeah, the standard
not
stuff.
just one kind. Scientists have actually cataloged over 20 distinct types of ice.
20? Seriously, I had no idea.
Yeah, each forms under different conditions, pressure, temperature, and it's not just, lab trivia, this complexity. It actually affects real-world things,
Like what?
like how bright clouds are, which impacts climate, how your frozen food keeps its texture, even just how frost forms on your windshield. Understanding all these ice types gives us a much deeper view.
Okay, so let's really get into this hidden world of freezing then. Because you said until just recently, those very first moments, right when water starts turning into ice, especially in tiny droplets, that was basically a black box.
Pretty much. A complete mystery, like trying to see the very first spark of a fire,
Mm-hmm.
but, at a molecular level. We knew it froze, obviously, but how that jump from liquid to solid actually kicked off wasn't matching our model.
A real blind spot. But now, these new simulations, they're pointing to ice zero as that first spark.
That's the idea, the crucial missing piece.
And here's the part that really got me. It defies what you'd think. It doesn't form deep inside the water droplet.
No, not at all.
Instead, these ice zero clusters, they gather just under the surface, like a tiny fraction of an inch below the boundary between water and air.
A few billionths of an inch, yeah, right there at the interface.
Wow, so these ice zero clusters are kind of like the initial scaffolding,
Yeah.
the staging ground where regular ice then starts to build.
The great way to put it, the first domino. And this breakthrough comes from a team over at the Institute of Industrial Science at the University of Tokyo. They published it in Nature Communications.
Ah, okay. Big deal journal.
Definitely. And what's really significant, beyond just finding ice zero, is that this work settles a really old scientific argument.
Oh, which one?
Well, for ages, researchers debated, does that bare water surface actually help ice start forming, or does it get in the way, suppress it?
Right, I could see arguments for both sides.
Exactly. Theories went back and forth, but these simulations, they pretty clearly show the surface encourages it. It's the preferred spot. The lead author, Gang Sun, put it nicely. He said, simulations have shown that a water droplet is more likely to crystallize near the free surface under isothermal conditions.
Isothermal meaning
Yeah,
same
yeah.
temperature throughout.
Yeah, uniform temperature. And he added, this resolves a long-standing debate about whether crystallization occurs more readily on the surface or internally. So, a clear answer.
That really does flip what I would have guessed. You think of freezing starting from the inside or just happening everywhere at once. So if we know where it starts now, near the surface,
Yeah.
what is this ice zero? What makes it so different from, regular ice?
Well, looking at it in the simulations, it doesn't look quite like that perfect, rigid ice crystal. It's described as looking sort of halfway between liquid water and that neat lattice on a skating rink.
Halfway. How so?
It's the molecular structure. Regular ice, it's made of these perfect six-sided rings of water molecules, very orderly hexagons.
All right.
Ice versa. It's messier. It's a mix. It has five-sided rings, six-sided rings, even seven-sided rings, all jumbled together in its network.
5, 6, and 7. That sounds unstable.
Well, messy might be a better word. And that messy structure is actually the key to why it forms first.
How does that work?
Think about it like this. For water to lock into that super orderly, solid ice structure, it takes energy. There's an energy cost or barrier to overcome.
Okay.
This mixed ring structure of ice zero, it actually lowers that energy cost. It's like an easier first step.
Sure.
Less energy needed to form this slightly disordered structure from the liquid compared to jumping straight to the perfect ice arrow.
Ah, so it's like an easy entry point for freezing. Water tries this simpler structure first before committing to the full crystal.
Exactly. It's the path of least resistance, energetically speaking, to start becoming solid.
That makes sense. An easy entry. And you said it forms right near the surface. Does that messy structure link to the location?
It does, yeah. It connects back to surface tension. That stretching force at the water's surface creates this tiny bit of negative pressure right underneath.
Negative pressure like suction.
Sort of, yeah. Slight stretching. And that specific condition, that negative pressure near the surface, seems to make it easier for these mixed 5, 6, and 7-membered rings to pop up, more so than they would deeper inside the water.
Fascinating. So the surface conditions actually favor this Messier intermediate step.
Precisely. Now, you might be asking, if it's the crucial first step, why haven't we actually seen it before in labs?
Yeah, that's the big question.
The challenge is just immense. Trying to track individual molecules moving that fast, it's almost impossible with current lab tech. Like watching one specific spark in a huge, chaotic firework display.
Okay, so direct observation is out. How did they find it then?
They use something called molecular dynamics simulations. Basically, super powerful computer modeling.
Right, like a digital microscope.
Kind of, but dynamic. They didn't just model a few molecules, they simulated hundreds of thousands interacting over time. They used a specific model called the MW water model.
MW.
Yeah, it was a smart shortcut. It keeps the basic tetrahedral shape of water molecules, which is vital for how water behaves, but it simplifies the complex electrical charges. That made the simulations way faster.
Ah, speed versus perfect detail, but keeping the important bits.
Exactly. It let them run hundreds of simulations long enough to finally catch these really rare, super fast freezing events, something that might take years to maybe see once in a lab.
So it wasn't just about computing power. It sounds like they needed a whole new way to even look for it in the data. You mentioned a new yardstick.
That's perfectly put. A new yardstick was essential. See, older studies looking for ice-use tools, metrics, that were basically designed to only spot those perfect hexagons of normal ice.
Okay.
So if your tool is only looking for hexagons, and I0 comes along with its 5- and 7-sided rings mixed in.
You're going to miss it completely. It doesn't fit the template.
Exactly. So these researchers developed, or, well, chose a different tool. An order parameter sensitive to 12-fold correlations. Fancy name. But the key thing is, this new metric didn't care only about hexagons. It gave equal importance to the messy bits in I0 and the tidy hexagons in I-Sayer.
Like a more versatile scanner.
Perfect analogy. And that methodological shift was crucial. It let them finally see I0's signature in the simulations, confirming it was there. Without that new way of looking, it would have stayed invisible.
It really shows how the tools we use shape what we can discover.
Okay, so they found it with simulations and a new way to look, but there's another reason it was hidden, right? You mentioned it's fleeting.
Incredibly fleeting. It basically doesn't last. Think of it like a chemical primer or a catalyst. It kicks off the freezing, and then poof, it's gone almost instantly.
How instantly are we talking?
Picoseconds.
Yes.
Billionths of a millisecond. It serves its purpose as the starter nucleus, and then it immediately transforms into the regular ice eye, the common ice we know.
Wow, okay, no wonder experiments missed it. They'd only see the final product, the ice eye.
Precisely. Direct experiments usually detect the stable final structure. They completely miss this critical first step, this hidden prelude. It's like seeing the cake but having no idea someone first whisked the eggs.
And interestingly, even though ISO vanishes, the spot where it formed matters.
Yeah.
The regular ice still grows from that same subsurface zone. That's right. The transformation happens so fast it basically locks in the location. The final ice crystal still prefers that region just under the surface where I0 gave it the nudge. It sets the starting point.
And that detail, that location preference, that has big implications.
Huge implications across several different fields, actually. Let's start with climate studies. This could be really important.
How so?
In the atmosphere, think about clouds. Sometimes you get super cooled water droplets, liquid below freezing. Whether they stay liquid or turn into ice crystals makes a massive difference.
Right. Ice crystals make clouds brighter, reflect more sunlight.
Exactly. And a tiny temperature shift, tenths of a degree, can trigger that freezing. If I0 makes freezing easier near the surface, climate models need to account for that. They can't just treat water droplets as uniform blobs anymore.
So the outer shell of the droplet is like a special zone for freezing.
A privileged zone, yeah. Building that in could really refine predictions about cloud brightness, how much precipitation forms, which ultimately improves our climate projections, especially for those high, cold, cirrus clouds made of tiny droplets where this surface effect would be dominant.
Okay, climate makes sense. What else? You mentioned food.
Yeah, food science, it sounds different, but the physics is similar. Think about flash freezing berries or making ice cream.
Ah, trying to avoid big, crunchy ice crystals that ruin the texture.
Exactly. Nobody want mushy strawberries or gritty ice cream. This research suggests that encouraging fast, surface-started freezing, like ice deer does, might actually trap water in smaller crystals, preserving that texture and flavor better.
So, understanding ice hero could lead to better frozen food and maybe save energy in the process.
Potentially, yeah. New freezing methods that leverage this could improve quality and maybe even cut energy costs for food processors. A win-win.
Okay, climate, food, any others?
Well, think about the refrigeration industry. What's their constant headache?
Frost. Building up on coils and stuff.
Bingo. Frost buildup kills efficiency, wastes energy, needs defrost cycles. If ice shear is the first step in frost forming on those surfaces,
Maybe you could design surfaces or coatings that stop ice arrow from forming in the first place.
that's the idea.
Yeah.
Disrupt that very first denucleation step. It could delay frost significantly, meaning longer times between maintenance, better energy efficiency for everything from your fridge to industrial coolers. Like the senior author Hajime Tanaka said, these findings about surface crystallization, they're expected to contribute significantly across fields like climate and food science where ice plays such a critical role. The impact is surprisingly broad.
It really is. So wrapping this deep dive up, the core idea is just mind-blowing, really. That tiny, thin layer right under the skin of every water droplet, that's where the secret to freezing lies.
Yep, the key is right there at the boundary.
And Ice is this quiet, super fast player that kicks the whole thing off. It totally rewrites how we thought freezing even began, revealing this hidden, vital first step.
It's a fundamental shift in understanding.
It's just amazing that something so common, happening constantly all around us, held on to such a deep secret for so long.
And the exciting part is, this is probably just the start, now that simulations have pointed the way.
The race is on to actually catch it in the lab.
You bet. Scientists will be using ultra-fast lasers, powerful X-rays, trying to essentially freeze time and get a direct snapshot of ice zero forming and vanishing, turning this simulation into experimentally confirmed reality.
That'll be incredible to see.
It really makes you wonder, doesn't it? If water freezing, something so basic, had this hidden layer we just uncovered, how many other everyday processes have these quiet players, these hidden mechanisms, shaping things in ways we haven't even thought to look for yet?
What other common things have secrets hiding just beneath the surface, waiting for the right yardstick to find them?
Exactly. Makes you look at the world a little differently.